Okay, so we're talking about radioactivity. And this was discovered, let's see, I don't remember the dates. You can tell I don't remember particular dates myself, so I'm never going to ask you for particular dates. I do look sometimes for chronologies in terms of like putting events in order. This was Antoine Henri Becquerel. I don't know if I'm pronouncing his last name right. 1896, discovered radiation or discovered radioactivity by accident, as so often happens. Of course, these things are never like totally by accident. You know, sometimes it appears the way we talk about these experiments, it almost seems like every time these discoveries are made, like totally by accident, somebody's like, wow. No, they were typically doing some sort of an experiment that was somewhat related, right? And something happened that they didn't quite expect. Like in the case of the discoveries of X-rays, he was working with photographic plates, and he noticed that some of them were exposed in cases which he didn't expect. This was similar. This guy was doing experiments with uranium. In fact, apparently he was doing experiments to see if uranium that had been exposed to sunlight would then expose photographic plates. So I don't know if he thought it was like absorbing light and then giving it off again or something. But what he noticed is that even uranium samples that had not been exposed to sunlight were exposing photographic plates. And these other two folks, Marie and Pierre Curie, took that information and they started to do further experimentation, okay? They called this phenomenon radioactivity. The energy that was given off was called radiation. The energy given off was called radiation. Okay? And they isolated some radioactive elements also. And the three of them together, I think, won the Nobel Prize back then at one point for their work. But they worked a lot with radium, so they isolated radium, and I can't think of the other element right now, but these are elements that are much more highly radioactive than uranium. And it turns out that back then, as is always the case, people don't realize that things are harmful, right? When Rontgen first discovered X-rays, and this was a little before this, I think, I don't know the date. Yes?
Didn't they have, even for shoe sizing, they had those machines where they would size up your foot based on the X-ray? When you never
Right.
take your shoe off?
They could X-ray you. Yeah, they would actually have like parties where they would bring like the X-ray machine, and it'd be like just a fun thing to do at a party. Like everybody get X-ray themselves. Like you want a picture of your skeleton to take home with you? I mean, seriously, that's what they were doing, because they didn't know it was harmful back then. Now, when you get an X-ray at the doctor, not at the doctor, say at the dentist, right? You go twice a year, they point that thing at your head. What do they do first? They put something on you. What is it? Lead. Right? Of course, then they shoot the X-rays right at your brain, right? But they cover your chest with lead. And what does the dental hygienist do? She leaves the room. Now, so here's the thing, folks. For you, apparently, the exposure's okay because you're only getting it once or twice a year, right? For her, she would be exposed to the same level of X-rays, several times a day at least, probably every day. Yes.
But you get exposed to more radiation at the beach though than you would not like X-rays.
Not X-rays.
In the sun, though.
Yeah, but I don't think it's not ionizing radiation like X-rays are. So it's not. I don't know. As far in terms of potential harm, you mean?
Yeah.
Yeah, I'm not sure how that would balance out. So these two were similar folks. They both ended up dying of cancer. And it's said that their whole lab actually glowed with a faint light when they shut the lights out. That everything had become radioactive. Radioactive decay has a way of making other things radioactive, as we'll see later on. When particles come out of nuclei, they hit other nuclei, and they can make those radioactive as well. So it kind of, everything became radioactive. They're working with these purified samples of radioactive elements. That's what they were doing. That was their research. So they didn't know this was going on. The same thing with phosphorus, by the way. The guy who discovered the element phosphorus, phosphorus is really cool. We'll see it, some demos of it later on this year. It's like a white waxy element that if it's in a thin film, like if you wipe it on your face, it glows in the dark. It produces a greenish, eerie kind of glow. When they first discovered it, they would do the same thing. He would go around and have like phosphorus parties, and everybody would like paint it on themselves and glow in the dark. Little did they know how toxic it was. They didn't realize it at the time. So there are, first of all, let's look at this, I guess. What is radioactivity? Radioactivity is, I guess you could say, the breakdown of a nucleus, okay? It's when a nucleus is breaking down. So nuclei breaking down, okay? We sometimes call it radioactive decay. Okay, radioactive decay. The nuclei are unstable. And by the way, not all nuclei are stable. A lot of them are stable. So like carbon-12, for example, does not do this. Okay? Carbon-14 does. So some isotopes are stable. So we say that the nuclei are unstable. And to start with here, let's ask this question: what determines if a nucleus is stable or not? Stable or not? Well, let's take a look at, let's see. I think I've got a picture of it here. It turns out that it is the neutron to proton ratio that determines whether a nucleus is stable. There's that ratio thing again. Darn it, I thought we were through with that. Thought I opened this, sorry. Alright, why isn't it opening up? Sorry, this thing's supposed to be opening for me here. It's not. I have to edit this out. All right, I'm going to do this. I'm going to draw it for you. You can refer to your book on page 845 for this figure. I don't know. I'm having trouble pulling the picture up, so I'll just draw it. If we make a graph and we put number of neutrons on this side, and we put number of protons on this side, and we say, so what we're going to plot is the isotopes. We're We're going to plot the stable isotopes, fellas. We're going to plot the stable isotopes like this. Oh, go ahead and take a break, folks. We will continue when you return.
Go.
This is the figure that I was about to draw. Number of neutrons on the left, number of protons on the right. And what you see here, first of all, they show you a line which represents a 1-to-1 neutron to proton ratio. These red spots, the red dots on the figure, represent stable nuclei. These are non-radioactive isotopes. So you'll notice that, see how there's a whole string of them along this vertical line? Those are all the same element. There's, 7 different isotopes of that element. These are the stable isotopes all plotted out on this graph. What you notice here is that this so-called band of stability that curves up here, it breaks away from the 1-to-1 line around element 20, which is calcium. So basically, the way it works is this. Up until about the element calcium, there's a 1-to-1 ratio of neutron to proton in a stable nucleus. In other words, in order to have a stable nucleus, you want roughly the same number of neutrons and protons. And you can verify this if you look at the atomic numbers and the average masses. For calcium, atomic number is 20, the average mass is 40. Right? So that indicates about a 1-to-1 ratio of neutrons to protons, 20 protons, 20 neutrons. But by the time we get up to uranium number 92, atomic number is 92, and the mass is 238. So you can see now we're up to something more like a 1.5-to-1 ratio. See that? That's what's stable. Now, if there's an isotope that is outside of this red band in terms of its neutron to proton ratio, then it becomes unstable. It can no longer hold itself together. So the whole balance of forces inside the nucleus becomes such that the thing will just spontaneously start to break apart. Now that diagram is on page 845, so you can take a look at it on your own. But now I want to talk about 3 types of radioactive decay. Three types of radioactive decay. We're going to start with kind of the simplest one, most straightforward type, and that is called alpha decay. Alpha decay, and this is just an example. There's a lot of different elements that can decay through alpha decay. This is just an example with uranium-238. So this is an isotope of uranium. Now this type of notation here, the way I just drew this symbol is the way we're going to be writing, designating isotopes, or what we call nuclides. Typically we use the word nuclide for these isotopes. We're focusing now on the nucleus. We don't even care if there are any electrons at all on this atom at this point. All that matters is the nucleus. So that's what we're focusing on in this part of the unit. Remember, this right here is the mass number. This is the mass number, which is protons plus neutrons. And this, of course, is the atomic number, which is protons only. So this is the way we're going to be writing the isotopes. And then we show a reaction, just like we would a chemical reaction. The arrow means yields or produces. It's kind of like the left side is before, the right side is after. Before, after, before, after. So before we have uranium-238. After, we get thorium-234. And a helium nucleus. All right, now, a couple things about this, some terminology first. On this side of the equation, this is called the parent isotope. And this one here is called the daughter this helium nucleus is the alpha particle.
But wait, so only the pH is the
Right.
okay.
Alpha particle, we can use the little Greek letter there. Now, you might have heard of alpha particles before because a certain scientist used them in a certain experiment that he did when he shot them at something. Rutherford shot them at gold foil, right? Now, he didn't actually know what they were at the time. You can kind of follow the sequence here and the connections between things. Apparently, this was after the discovery of radioactivity, right? And Rutherford knew enough about this radioactivity this radiation that he knew it was positively charged and that he could accelerate it through gold foil. But it's coming out, in this case, from the uranium nucleus. And the alpha particle is identical to the nucleus of a helium-4 atom. 2 protons, 2 neutrons. It's that simple. But what I want you to notice now is look how the numbers add up. Uranium-238 makes thorium-234 and helium-4. 234 plus 4 is 238. Right? Look at the atomic numbers. They add up too. 90 plus 2 equals 92. This is always going to be true in nuclear equations. In nuclear equations, mass numbers and atomic numbers must add up. On the left side must equal the right side, okay? Left side of the equation must equal right. So whatever's on the left side must equal what's on the right side. Let's talk about the second type of radioactive decay. It's called beta decay. Beta decay. Now, an example of beta decay is this one here, which you've probably seen before. If we take carbon-14, carbon-14 is used for radioactive dating. It's used for radiometric dating, of organic materials.
Wait, so the thing you said before about the nuclear particles, remember how they must add up, like 234 plus 4 equals 238, like the mass number and the atomic numbers have to add up, right, from the reaction.
Mm-hmm.
That's for all of them?
Yes.
Not just for the different types of radioactivity?
No, that's for everything. Yep, including beta decay and, as you'll see, other types of nuclear reactions as well. Now, carbon-14 decays and becomes nitrogen-14. And first, you got to appreciate what's going on here. We're actually changing, well, we're not doing it. It's doing it by itself. One element is changing into another element. Okay? This is not an ordinary chemical reaction. In this case right here, in number 2, a carbon atom is actually changing into a nitrogen atom. This is what the alchemists were doing. What they thought was possible really was possible. It's just they weren't taking the right approach. They didn't have nuclear reactors and so forth to make new elements. But this is not done because, as you can see, the numbers don't add up now. Look at that. I'm okay with my mass number. Now watch what I can do here. I can kind of I can actually figure out what's going to be on in the next place here to some degree. I know that its mass number must be 0 because I know that 14 must add with this to produce 14 because my numbers have to add up. So I know that the mass number is 0, and look at this. I know that I'm going to have to write a -1 for the atomic number. Well, what is that? Turns out it's identical to an electron, right? And it is called a beta particle. A beta particle. Now, this is where things start to get a little bit strange, and they continue to get stranger as we move on in nuclear chemistry. But if you look carefully at this, you can see what happened. Yes? Yes. A beta particle is identical in properties to an electron, except that it was not outside of the nucleus, nor was it inside of the nucleus. The beta particle came into existence during this process. Came into existence when a something changed into something else. Fill in the somethings. A something changed into a something, and the beta particle came into existence at the same time. What am I talking about? Listen. Very good. A neutron changed into a proton. So look at this. Look at the atomic number. Look at the mass number doesn't change. So in other words, the sum of the protons and neutrons stayed the same. The total number of nucleons, total number of nucleons, we're not talking about, nucleons are nuclear particles, protons and neutrons, okay? The total number of nucleons, protons plus neutrons, stayed the same, okay? But what happened is a neutron turned into a proton. So, now think about it. Something that was neutral became positively charged. How did it do it? It did it by coughing out something that was negatively charged. It spit out, like a hairball, a negatively charged particle, which was like an electron, okay? So it's kind of weird, but this is where, you know, when you get down to the atomic level, things stop acting according to what we would call common sense. They really do. Let me give you another illustration. One of the weirdest things about nuclear decay is that you can't predict it. You can predict it statistically in the sense of you can say there's a certain probability that this atom will decay within the next half hour, or within the next 5,730 years, say, in the case of carbon-14. There's a 50% chance this carbon-14 atom will decay within the next 5,730 years. But I can't say any more than that. Now here's the thing, folks. People used to think that this meant that we just didn't know enough yet, that we just don't know enough about what's happening in the nucleus. Certainly, if we knew enough about inside the nucleus, we would be able to predict exactly when that thing's going to decay. If we could look in there and see the particles moving and see, oh, now we know what makes that thing decay, we can predict it. Not true, okay? The current state of physics, and it's been 100 years now that they've been working on this problem. The current state of physics is that it is not possible to know it because there is no cause. There is no reason that it happens now rather than later, or later rather than now. Okay? There is no reason that it happens at a certain time. So anyway, we'll talk more about that as we get to electrons. So this is all kind of weird stuff, and it gets weirder. What's the third type? The third type is kind of different than the other two. It's called gamma. By the way, there aren't just three types of radioactive decay. There's only three we're going to talk about, because your book only discusses three, I believe. Yeah. Gamma decay. Now, gamma decay is kind of an extra thing. I'll show you what I mean. If we start with 230, thorium-230, and this is atomic number 90. This will decay into radium-226. That's the element that the Curies were famous for. And that's atomic number 88, plus an alpha particle. And gamma ray. Now, a gamma ray is just a wave of electromagnetic radiation. Okay? It is high energy electromagnetic radiation. Now, here's the thing. It's not a particle. Okay? So it doesn't have an atomic number, mass number, anything like that. In fact, you'll notice it doesn't affect the other numbers at all. It doesn't affect the other numbers. So you would never actually know that it should be there. If I hadn't drawn that gamma there, if I hadn't written it there, you would not realize it should be there. And so you are not going to be held accountable for figuring out whether there should be a gamma ray coming out or not. All right? We just want you to know that it does often come out during radioactive decay. And the reason it's important is because it's very high energy. Gamma rays are higher in energy than X-rays, which are higher in energy than ultraviolet rays. So it goes UV, X-rays, gamma rays in terms of energy level. All right? Now let's talk about that a little bit. If I had a radioactive source in say a lead box, kind of like Rutherford had, and so out of here are going to shoot the particles. So I'm going to have an alpha particle coming out of here, a beta particle, and let's make this hole a little bigger, and a gamma ray. Now I want to see which one's stronger, right? How do they behave? So I'm going to put a piece of paper here first. I'm going to put a piece of paper here, and what I find out is that the paper actually stops the alpha particles, but the beta particles go right through. The beta particle goes through the paper, and so do the gamma rays. Now, if I want to stop the beta particle, I'm going to have to use something a little thicker, like maybe a piece of plywood. Okay? So I'm putting a piece of wood here now, and the wood is going to stop the beta particle, but the gamma ray is going to go right on through. If I want to stop the gamma ray, talking about like a chunk of concrete. So this is concrete, or maybe lead. Right? So I need something more dense, more substantial, with more mass to collect these things. And you know what? Even then, I might still get some gamma rays leaking through. So these babies have some serious energy going on. Now here's the thing though, you can look at a diagram like this, and this by the way is in your book on page 844. You can look at a diagram like this and you can say, oh, then we don't need to worry about alpha particles, right? Well, not so. Because let's say in your house, and this is true in a lot of homes around here, you have this basement, and there's cracks in the basement walls, and down here in the bedrock, there's all kinds of elements down there, right? And there are metallic elements that decay into something called radon gas. Radon gas is radioactive noble gas. Don't think all the noble gases are kind, okay? Radon gas leaks up into here, and usually when you sell a house these days, they'll do this little test. They put a canister in the basement. It sucks in air for a period of 24 hours or something like that, and then they test it. And then they can certify that this is radon-free home, or if you got problems, what they do is they'll put a ventilation system in, something like that. Radon gas. Let's say radon gas decays, and I'm just making this up right now because I'm not sure the paths that radon gas decays along. But let's say it decays by alpha decay. First of all, and here's the kind of problems you're going to have to do. What should go there? You have a question? You want to answer? What goes here? 218 and 84. And then you look on the periodic table, you find number 84, polonium. Okay? Polonium. Not bolonium, as some of you were thinking, I'm sure. I know what you're thinking. You're thinking, oh, this whole class is bolonium. But bolonium does not exist. Okay? So it's polonium. Now, one of the things that's kind of neat, if you look at the periodic table, when you have alpha or beta decay, you can actually watch how it's shifting across the periodic table. So like in this case, we started here with radon. We moved back 2 clicks to polonium. So it's almost like you can trace around the periodic table these different decay paths. And usually there are a whole series. Like polonium-218 may be radioactive, so that might decay into something else, which might decay into something else. And there may be a whole series of reactions. But if radon is a gas, well, here's me, right, sitting in my house. Maybe I'm at the computer, and I'm breathing, right? And the radon's going into my lungs. Well, here's the thing, see, this is why I say you can't just look at this diagram and say, oh, it's not dangerous, because sure, a piece of paper will stop alpha particles, but there's no paper protecting the alveoli in my lungs from that radon gas. Now, how does radiation harm you? Those little particles are not just floating gently out of the nucleus. They come out of there like that. They pack a punch. They come flying out of that nucleus. Once they break away there, electromagnetic repulsion takes over, and those things are going like flinging out of the nucleus. So they're flinging out of the nucleus, and they're hitting things like, oh, lipid bilayers and proteins and stuff like that, and they're just pummeling them, right? And that kinetic energy is getting transferred just like a bullet into those particles, and they're getting smashed to smithereens. And so there's damage going on over time. What if you were breathing some dust? What if you were a person that lived in Hiroshima or Nagasaki, and for years and years afterwards, you're breathing dust that includes radioactive particles? And that dust is going into your lungs, and you're ingesting it. It's in your stomach. And those alpha particles are just coming out from those atoms, and over the course of your entire life, bombarding the tissues in your body with radioactivity. That's where it's dangerous, right? Now, it could be beta decay as well. By the way, I forgot, I was supposed to run over and get the Geiger counter. We're all being exposed to radiation even now. If I had the Geiger counter, I'd hold it up, it'd go click, 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 click. And that would be radioactive particles from our environment in this lab right here, just from the counters and from the air hitting that thing. So we're always exposed to what's called background radiation, right? The big question is, how much, are we exposed to elevated levels? All right? So that is, what did I get to? I got to gamma decay, yeah. Let's try some of these, right? These are fun, these little problems that we can do. So let's try some more before we move on to fission and fusion. So I'm going to give you some of these little decay equations to try. Okay, blank goes to a beta particle and cobalt 59. Now you need a periodic table to do these, folks, because you can't just write the numbers, you got to write the element symbol down. So you're going to need a periodic table to look at so you can figure out what should go there. Let's see. -233. just going to write a few down, then we'll talk about them each. This is supposed to say 90 here, sorry. Okay. Who's got the first one? Tom? Iron? What are the numbers?
26 and then 55.45.
Well, we want to put a mass number in here, not an average mass. So you just add these up, right? 59. Right, these are mass numbers, so don't put the atomic mass from the periodic table, because remember, that's an average. These are particular isotopes. All right, how about this one here? Next one? Joey? NP? So the mass number is 237 and 93. Does this add up? 233 and 4 is 237, 91 and 2 is 93, right? Okay, how about the third one? Martin. Oh wait, I messed up. Who caught the mistake here? It's not helium 0, it's helium 2, right? Sorry. Okay, so this would be uranium, would it? You got to take 90 minus 2, right? So it would be 88, right? Actinium? No. Radium, sorry. Where's 88? Yeah, 88 is radium. Whoops, that's the atomic number. And 230, no, 226. Okay, next one. What's the last one? Yes. 83, right. Okay, good. So there, remember folks, don't lose sight of the fact of what's going on here. Lead is turning into bismuth. If you had a big chunk, if I had a big chunk of lead 210 here, and it was all lead 210 isotopes, also remember that 210 is not the average atomic mass. That 210 is called the mass number. It's a particular isotope. It means there are 82 protons and 210 minus 82 neutrons, however many that is. So if this whole thing were made of pure lead 210 isotopes, then in a certain amount of time, probably a very long time, if I came back in millions of years, this might be pure bismuth, or almost pure bismuth. One element changes into another, and over the course of that time, this would have given off a bunch of beta particles. So that's the sort of problem you're going to have to do with these. You'll be given blanks like that. You'll have questions where you have to sort it out and figure out what's the parent, what's the daughter, what's the decay type. So I might give you a question where I don't give you the decay type. You know, that's another type. So let's see. The daughter is americium-241, which is, where is it? 95. We don't know what kind of decay it is. but the parent is plutonium 241. What type of decay is it? What's that? Look what happened. The mass number didn't change, and the atomic number went up by 1. Now there are other types of radioactive decay. There's something called electron capture, which is kind of like beta decay backwards, where the electron comes into the nucleus. There's something called positron decay. A positron is basically a positively charged electron, and so it's kind of the opposite of beta decay in another sense. So there's all different ways that this can happen. These are all radioactive decay equations. Okay, questions on those? Is that enough practice? All right, how about more movie? I'm tired of talking.